Good morning, everyone. First of all, this is quite separate maybe from the first part. So the tutorial is about GFF and SLE, and yes, they are related. But I think my main goal still is first to try to make sure that you have some idea what SLE actually is. And then you can start believing that GFF and SLE are actually related. So somehow, originally SLE was introduced to describe scaling limits of interfaces, like we already heard in some earlier talks. So yeah, I think that the topic will be actually like what is SLE? So we already know it's an acronym. Right? Due to Schramm and Loewner. So Loewner was a complex analyst who was working a bit more than 100 years ago on some growths of planar sets. And he developed a theory that's actually very, very useful in planar geometry and planar random geometry. And then Schramm had the idea that how about making this growth random by introducing some kind of universal driving process that turned out to be Brownian motion in order to describe these critical interfaces. So let's see. So the original motivation of Schramm let's say interfaces in planar. So I'm not able to say anything about higher dimension and maybe critical because we expect some conformal symmetry models, often discrete, but not always. So we heard yesterday that there is a continuum GFF object, and you can also kind of associate interfaces to that. So that would be some kind of model in the continuum. But it's easier to think from the discrete.
What is critical?
What does critical mean? Yeah, exactly. So this is maybe a physics term. It refers to some kind of property where you expect conformal invariance to hold in the scaling limit. So I want to give you an example, which is the Ising model. And maybe there you can somehow see what the critical word means.
But the white noise is also conformal invariant.
No, planar Brownian motion is. But yeah, so you have to interpret this in loose terms. So maybe, so what does it mean? Critical. So in the sense of that we expect, maybe I should say scale invariance or actually conformal invariance. Of some sort. Yeah, so this is going to be a lot of kind of heuristic ideas because this area of objects and research is actually extremely technical when you go to the details. And I wish to try to give you more kind of the intuition of what's happening. And then you can look from books and lecture notes and we can discuss more, some detailed things. But indeed, this is some term coined by physicists. So what we expect is some kind of scale invariance. And let's maybe consider one example model, which is the Ising model. We could consider dimers, but it's hard to have interfaces in dimers. You can have double dimers if you like dimers, but it's harder to describe. So Ising model. So what do we have? We have some spins, right? It's a model of spins. Let's say sigma x, where x are vertices of a graph. Let's say, yeah. I'm just inventing some notation, so please ask if I'm being inconsistent. Okay, so our graph could be the square grid. And I want to look at some finite portion of it. So let's intersect the square grid by some finite, let's say, simply connected domain. So, for instance, Z2 intersected with, I don't know, unit rectangle, maybe like that. So for the purposes of the presentation, I hope the details are not so important so that you can follow. So maybe there should be one more layer now. Okay, so I'm pretending here was my unit cube, and then I've got some vertices. And at each vertex, I have a spin, which is a random variable. And they come according to some probability measure, right? You probably already know if you've seen these models before, or if you were in Nathaniel's talk on Monday, that there's a particular measure on these spins. So you can say that the probability of a spin configuration, so I should say maybe sigma x indexed by the vertices. So I should say, that the spins belong to plus minus 1 in this model. You can have more general models if you want. A question?
Yeah, so maybe the lattice should be scaled by some mesh size, no?
Yeah, so I didn't take scaling limit yet, but I was planning to do this, yes.
And what you're under, it's
very
c
small,
squared intersected minus 1 squared, so that's only...
Okay, this is a bit stupid. Maybe 1,000. Or, okay, let's scale it. Yeah, sorry. By delta, okay. And delta is some positive number. Yeah, thanks a lot. Like you say, it's very on a high level. So the point is that when delta goes to 0, this is supposed to be then becoming some kind of model of spins in a continuum domain, which is this square. And then you have uncountably many spins, so you cannot really make sense of these spins as a function. So it actually will look similar in the sense that we had for the GFF, that it can be described as some random distribution. So this is not the direction I will go. But the point is that in the scaling limit, you have to be careful. But when I fix the delta, I still have some finite system. Okay? And then I want to keep my rectangle fixed so that I have some fixed volume of the system. And I've got these plus and minus spins with some probability measure, which is going to be, maybe I just say proportional to, because you want to normalize them. But the normalization factor we will not need here. So now might need your help again. So I need to have a temperature parameter, beta. And I think there are two minus signs. So minus beta times the Hamiltonian, which has a minus sign. So I take the summation of next door vertices. So this means that xy is an edge. So this is a nearest neighbor interaction. Here I just multiply the spins at x and y. And beta is also a parameter. Maybe I should give it some color. Okay. Okay, so spins interact across edges. And each spin is plus or minus 1. So then this product is plus or minus 1. And depending on the parameter beta, you can see that the model has different behavior. So this beta represents inverse of the temperature. And I'm considering the ferromagnetic model. So let's see. So if beta is very, very small, then it doesn't really matter much what's here, right? So then the measure is almost somehow uniform. Everyone seems independent. So this should be the very high temperature region. So if you think about the Ising model in terms of some magnet, like physicists already originally introduced it, in very high temperature, the magnetization phenomenon is not there. So you have somehow disordered spins in your material. While if the beta is getting small, big, so the temperature is getting smaller, then actually the interaction is going to matter. And there's some special value of beta where you see some kind of phase transition. So if you make simulations of this model, I didn't bring pictures to this talk, but I think you can find them easily. There is a phase transition. Let's say with respect to beta. So that, maybe I can write here. So let's see, beta, what did I say? Very small means high temperature. So here is disordered. Spins almost independent. And beta, very big, is big, large, small temperature. It's very difficult. The spins want to be more aligned. So somehow, maybe it's not completely obvious from here, but when is this product +1? When both spins are the same, right? So in this low temperature region, the spins want to be the same. So one calls it ordered phase. So yeah, physicists talk about phases. And then here happens a phase transition. So there's actually a unique beta critical, which is some non-trivial positive number. This is called critical, let's say, inverse temperature. Where, well, I should say maybe critical phase here or something like that. Or, yeah, so now this is the word I was using there. Or I could say something like scale invariant. Referring to if you take delta to 0 limit, you actually expect some scale invariance. And if you make simulations, you really see that in the ordered phase, you get lots of clusters with the same spin. So if you have two colors, so I was meaning to put colors here, plus and minus 1. Here, you get this kind of picture that you have, if you remember these televisions we had before the digital time, where you had this kind of white noise looking, picture. So that's that. And in the middle, you get some macroscopic fractal clusters of spins. So yeah, so the model might look like that. You have your two colors in some way. And of course, now I'm just putting them randomly because my head cannot really simulate this very well. But hopefully you see the idea. And then there are many, many other models, of course, which people also call critical. And there are various ways to characterize them. But really, the thing important for us is that we expect scale invariance. And one way to kind of try to observe it here is that if I look at correlation of two spins at some points x and y, so let's say, I don't know, maybe here is spin x, and there is spin y. So how are they correlated? So I could ask about the expected value of the product, maybe minus the individual expected values. And in this critical region, so if the x and y points are going far away, you actually have a polynomial decay of this correlation. Instead of here, the correlation doesn't really decay because somehow the spins really want to be aligned. In the disordered region, the decay is exponentially fast, so they become really independent if they're far enough of each other. So maybe I can write here something like y minus x, and there's some usual power, is it alpha? So there's some kind of power law decay, maybe negative, in the distance. So that's one feature that you often see that maybe hints that you expect some scale invariance. So of course, it's not a mathematically precise definition, but maybe it's reasonable to believe something like that. Okay? So That's one example model. So Oded was actually Oded Schramm. So he was thinking of other models, like if you take the random walk and erase loops, you get the so-called loop erased random walk, which is also some simple, lattice path. And maybe somewhat miraculously, if you don't put any weights, it's going to be also having this kind of property. And it's been proven that these SLE processes indeed describe limit of the loop erased random walk. And there are various other models as well, also the ones related to the GFF. But maybe it's the easiest to describe in the Ising model, because now, so we have our configuration which have plus and minus spins, so there's the two colors. And then I could detect the color, the different clusters of spins of same color. For instance, here is blue and blue, hope you can see it, by just surrounding each cluster by some path. So in other words, for each edge where I have different spins, I will put a path in this way. So then I get some kind of collection of loops in this picture. And they are living on the dual lattice. And maybe the square lattice is a bit tricky because sometimes there might be some pathological stuff, but you hopefully see again what the idea is. So you can encode all the spin configuration. Yeah, this was one there. Into these loops, right? And that's a nice feature of this example model. So note, because it doesn't care about the temperature. So then you can ask how do these loops behave in the different phases. So spin configuration, which is this random guys, encoded into, let's say, lattice paths. Or in this case, it's just loops. So then if you want to study geometry of the model.
I'm sorry, these are just boundaries of the region.
Boundaries of the spin clusters, exactly. Hopefully I drew them correctly. I was trying to, yeah.
Well, the two red ones.
Yeah, so you need to.
There are two red ones, one labeled by sigma x, which is not.
Oh, this one. Ah, yeah, because it has the green stuff. Yeah, thanks. Yeah, and one more. Right. Yeah, somehow I was getting colorblind by the green things, putting everything in the same picture. Yeah. So these are just boundaries of, of spin clusters. Cluster of spins is the connected component of the graph with agreeing spins. Connectedness meaning connected, by edges. Yeah. So then the idea that you can get from here maybe is that you can study geometry of the model via these, let me call it some name, like L, because I don't want to write below here so that maybe you can see something. So geometry, again, what does it mean? Well, the geometry of the clusters. And now you can try to convince yourself that in this disordered phase, where the spins are very independent, what dominates is some tiny, tiny loops, and you don't seem to see so much maybe. But while here there are some macroscopic, interesting looking paths. This is also usually referred to as interfaces, especially if they are not loops but paths. So now I need to erase something and I will make another picture to get actually to SLE. So the point will be that SLE curves are related to these loops after you take this delta go to zero limit. Okay? So that was the idea. And this should hold for any so-called critical model, which once again is something that we expect scale invariance. And you have some kind of local interaction, which I was hiding. So here, obviously, the interaction was local. So you could complain about that if you want, but maybe let's not go there. Okay, so now, so if we want to take this limit, this is called scaling limit. So first of all, how did I set it up? Is that the volume, which is this rectangle, is always the same. And then just the grid is getting finer and finer. So this is different from what people call thermodynamic limit, which is an infinite volume limit, right? So note maybe, this is a side remark. Volume is fixed and finite. And in my case, it's this rectangle. This is easiest to draw. And then I have the grid there. Maybe now I don't draw it. And now, so let's also fix, because we are interested in the critical models, in at least for the purposes of this talk, let's take this critical temperature. And then the question is, so somehow which loops or paths in this L survive when, at this limit, right? Not all of them will survive, because the tiny ones that only surround one, for each realization, if you just have a small one, of course, it's not going to be visible in the limit. So you might want to somehow ensure that you see something. And one clever way to do it is to impose boundary condition. So because we have this bounded domain, there's boundary. And I could impose the simplest possible boundary condition, which is that I put given maybe plus spins on a certain segment. Let me do like that. And then minus spins on the other segment. I may have wanted to, well, it's an impressionistic picture. So I may have wanted to have something like that. And inside, so here you still sample your Ising spins. But now, if you look at the probability amplitude here, so there's this interaction across edges. So there are some edges that are next to the boundary vertices. So there, the boundary vertex will have fixed spin that I decided here. And inside is random, but I count the interaction, in the obvious way. So hopefully, it's kind of obvious how to implement the boundary condition. And then, so now you can think, what kind of stuff happens inside?
So is the critical value sensitive to this boundary and this boundary condition?
So here is not necessarily important yet, actually, because I can always do this. But then when I take the limit, I want to see something interesting. But yeah, maybe we can fix it slightly later. So I can draw here what should happen.
No, but just to rephrase, so is the value of the critical beta the same once you condition on the specific parts on the boundary?
So this only depends on the lattice, but it doesn't depend on conditions on the boundary. So for the square lattice is something explicit involving some square root 2, which I forgot. Maybe someone here remembers it. So this is lattice dependent, but you can show it's unique. This is already by Onsager a long time ago, if I remember correctly. And okay, so if we don't fix the beta yet, it's a great question. So what is going to happen? I will draw here. Not sure if I'm able to draw one of them, actually. So let's imagine we have this boundary condition. I just draw in this way, red and blue. So in the very, very high temperature, where almost everyone is independent inside, So how do the loops look like? So the loops will be tiny, but then you also know that because here is a minus spin and here is plus spin, you have to have some kind of path starting from here, right? Because the paths are supposed to be boundaries of these spin clusters. And also there has to be a path there, and then it's going to go somehow a lot. So this is the case I'm not so able to draw probably. So let's do like that. So because we are in the plane, your path is going to somehow connect these two points. And then there will be also loops in addition that I will not draw. Maybe easier to think is the low temperature, big beta. Remember, beta is inverse temperature. Because there, many of the spins near this minus boundary also want to be minus by this measure. And here they want to be plus. So there is again a path between these 2 points, but it's relatively straight somehow. It's going to maybe, and then it's going to somehow just converge to a straight line in the limit. While in this critical picture, we have something more complicated. So if you look at the simulations from some pictures in the internet, you see that there's some kind of fractal, more interesting looking curve. So it becomes fractal in the limit, because in the lattice it's a lattice path. I'm drawing it continuously because it's much easier to draw. So there's somehow different phenomenon in the different betas also for this boundary condition case. And so the point here was that if I put boundary conditions, fixed boundary condition plus minus, which is here is plus and there is minus. So we have here one path, at least one path, which we call interface. And now I should maybe draw it there. But I wanted to keep this measure still before erasing. So does it make some sense so far?
I'm sorry, I got totally lost.
Ah.
So what is this curve? Is it the boundary of the blue region that contains the boundary of the domain, or is it the boundary of the red cluster that contains the domain?
If I make one more picture here. So this was a boundary condition I imposed, and then the other one.
So there is a cluster that contains the blue lines, right?
And then here, typically, so if I sample the spins in the grid, there will be some blue somewhere, and well, in many places, and some red, and so on. So what you can do, you can start looking from here, because these paths were supposed to go between the plus and minus spins. You will always see, you can explore, so that's a key idea for defining these SLE curves, actually. Where do you have minus spins on the left-hand side and plus spins on the right-hand side? And modulo some nuisance that may be lattice effects that I'm trying to hide here, you will find your path in this way. So there might be in the square lattice some stupid situation that maybe you have, that's the wrong color. You have something like, you don't know where to go if the spins are in this way, and then you're going in between, and now you could go either there or there. So you have to somehow make a choice what to do there, but that's okay. So modulo that, you will find this.
Not depend on the choice?
So the limit is not depending on the choice, but it's a non-trivial.
What if I make a random choice?
What's that?
What if I make a random choice?
I think you can make a random choice, because you can prove that somehow the minimal and maximal choices don't affect it, and then any random choices in between. So minimal and maximal being like, go to the rightmost possible place or leftmost possible place. So it really doesn't matter, but it's causing some headache if you try to draw these things on the square lattice. But if you believe me that it's going to be fine, you will find that this is ending there. So it's just part of these paths that was boundaries of the spin clusters. Okay?
Sorry, and what you were saying about the different choices, that's only for critical beta and frozen case, or is it also true in the disorder
Let's
too?
see. So I only ever considered the critical one, and there I know is true. For the other cases, let's see. So does someone know if the limit has been considered in these cases actually rigorously?
Yeah,
I think.
yeah, it's Brownian
Yeah.
motion. So if your
Ah,
scale
right.
stays like square root, then it's Brownian motion.
And it doesn't depend on the choice. Yeah, I mean, that's what you would expect.
But it's a straight line to the first order, right?
In this
Yeah, but the fluctuation
And
is
the fluctuations
Yeah.
are a Brownian bridge.
Brownian bridge, yeah. Yeah, but somehow it looks like a straight line. Yeah, regardless of where you turn.
I think this goes back to Dobrushin.
Yeah, probably. Yeah. Yeah, so this boundary condition, by the way, is called Dobrushin boundary condition.
And then when beta is very small, what happens?
So if the beta is very small, yeah, so this is going to go somehow, quite a lot. So I think it's believed that if beta goes really to 0, you should see critical percolation, but I'm not knowledgeable to say if there's any results on that front. I think there's no result, yeah. So it's somehow very, going everywhere. So anything in this region about the interface, I don't know if anything has been proven, probably not. Yeah? So there are some loops that I was not drawing, so we want to ignore them, because the point was that I want to make sure that when I take the limit, so I was somehow over here, the scaling limit, I want to make sure that there's some object I can study that's there for all scales. And now there are various kinds of loops, but somehow it's hard to look at them in a limit because the graph is changing, right? So then what's useful is that if I only consider that path, I know that it's always there for any delta mesh size. So it's a trick to be able to consider something kind of well-defined. So there are works also involving the loops, but I think it goes beyond what's supposed to be in the tutorial, so I was not going to talk about that. So now I will erase the definition. Actually, only you need to remember maybe is the different behaviors and that we expect some scale invariance. So maybe just for the terminology, because we are trying to set up a common ground. So this is called Dobrushin boundary condition. Is that if I have my boundary of, let's call this, it was a rectangle, but I can have it some kind of other domain. Let's say simply connected domain. So fix D, simply connected, and maybe bounded, just for purposes of not having any trouble. So then I can say that the boundary is divided into two segments, delta plus and delta minus, where here I say that sigma x is -1 for all vertices there, and here +1, right? So now I'm somehow identifying vertices, with the boundary segment, points on the boundary and so on. So this separation into two components, it was done by Dobrushin, and maybe he was actually studying these other regions, especially the low temperature region. So with this Dobrushin boundary condition, so we know that for any realization, there is a path, which we call interface, which is the yellow thing. Let's say I need some notation, maybe A to B, where A is one of these marked points and B is the other one. And now here, let's see, this is the delta minus boundary piece, and this is the delta plus boundary piece. from A to B in D, or maybe closure of D. And this doesn't depend on this delta mesh size, right? So that's the point of maybe looking at this special case, because now, of course, I have this delta grid here, yeah? And I have all kinds of loops, but let's ignore the loops, just focus on this one, because we often can call it gamma. And it depends on delta, because it's living on the lattice. So I was drawing it in a stupid way. I should have drawn it as a piecewise linear path, right? But I'm just lazy, so I'm drawing them in this way, because in the limit it's going to be some kind of, not piecewise linear, but not smooth either. Anyway, so now I have a well-defined object, right? So for the Ising model, for any beta, I can define this interface gamma when I impose the Dobrushin boundary condition. And now I can ask what happens when delta go to 0 to this interface, right? And now I really want to focus on the critical region for the reasons that here it becomes a straight line, here we don't know. So here we can say something, okay? So then, question would be, let's say, does gamma delta have a limit? And of course, you have to ask in which sense. So this is a random variable in some space of curves. And then one can get to very nasty business. Let me say suitable. So I was planning not to focus on the convergence itself, because it's really mainly a matter of technicalities if you believe that there should be some limit. But what you need to remember is that this is a random path, because it's coming from the probability measure of the Ising model, right? So then I need to look at it as a probability measure on some space of curves, and then talk about some weak convergence of those, if I want to be very precise, right? And then, okay, so does it have a limit, and what properties does maybe a limit have? Okay, and that's leading to this definition of the SLE. So this is really a useful thing to look at some geometric properties of the model. So I'm doing the simplest case here, but you can have much more complicated cases, of course, where you have more of these paths, and you can include loops and so on. But I think it's insightful to just look at this case. In principle, if I know all of the loops and paths, then I know everything, because then I know where the spins are, right? So this is really carrying information about the model in the scaling limit. And then especially if you ask about, like, is the scaling limit scale invariant, or is it conformal invariant? This guy should have that property, right? So one way to try to prove some features of the scaling limit of the whole model is to prove some stuff about these paths, right? So now let's say that we expect when beta was fixed to be this critical inverse temperature, maybe by some physics mumbo jumbo or this polynomial decay of correlations, that, let's say, law of this, because it's random, law of the limit, if the limit exists. So I may be writing very suggestively here. So this is conformal invariant. So not only scale invariant, but conformal invariant. And this expect is maybe a big kind of leap of faith. But actually, this has been proven by Smirnov and Dimachelka, who's one of the organizers of this thing, for the Ising model. And for many other models, there are also proofs. So you can somehow try to expect some properties from heuristic arguments and then try to prove them a posteriori. So that's somehow the route that we are often taking in this business. But maybe now you're wondering, what does conform invariant mean, right? So because this is a random curve, let's say, so now I want to call, I'm kind of supposing there might be some kind of maybe subsequential limit or something, and let me just call it gamma without any delta decoration, because I don't want to write all of this all the time. So now what we would have is that this gamma, this is a random curve. Let's write here. It's a random curve. So what does it mean? Curve in D. And then going between the 2 points, I was calling them A and B. So it's somehow indexed by this data, the 2 endpoints, and then the domain where it's living in, right? Which was the rectangle. And then I want to introduce some notation. So let's say it's has the probability measure that's indexed by these things in this way. So what does it mean to be a random curve? It means to be a random variable in some curve space that I didn't specify. So in other words, there's a probability measure or a law for this one. And now I can ask, what happens if I change the rectangle to some other shape? So the idea of this conform invariance, that maybe I abbreviate CI, it just means that if I had my maybe D here, and it's simply connected, so I can find a conformal map sending to any other place, the disk or whatever, maybe phi. So this is maybe phi of D, conformal map. And then I had these points A and B. Forgot, maybe this was A and this was B. So they go to some phi A and phi B. So I can fix if I want or whatever. So I know that here I have this gamma, which has this law. So now I'd like to draw here, but it's maybe not so great. So then I can ask, what is the law in the image side? And I'm claiming it has a similar form, but I just changed the domain and the marked points. And in other words, I can say that if I understood what the law of the random gamma is here, I can just push that forward by this map. You can push measures forward by maps, right? So then here is just the push forward measure. It maybe sounds fancy, but the point is that we really only need to study it in some reference favorite domain, and then elsewhere we can send it by conformal maps, and we know what happens. So that's the conform invariance property, that somehow the domain kind of essentially doesn't matter in a sense. And this is this big leap of faith that may be very mysterious at the moment for you. At least it's been mysterious to me all these years. But it's something you can prove for this limit. And I forgot if it was mentioned that the Gaussian free field is also conformally invariant. So you have this kind of so-called level lines for the Gaussian free field, which are also this type of curves. And they have this kind of similar property. So it's not specific to Ising model. So any critical model kind of should have this feature. Okay, so what have we been trying to do? So we've been trying to think, what on earth can this object be, right? So we could describe it in the lattice from the Ising model. It's a well-defined object, right? Imposing this Dobrushin boundary condition. And then I'm somehow hoping that there's a limit and calling it gamma. and asking what is this object? Can I somehow characterize it? And then I'm claiming you that one property it must have is this. And so in particular, then I can just study kind of one reference domain with two given endpoints of the curve. But this is not yet sufficient to characterize it. Maybe a side remark, if you're complaining about simply connected, you could consider more complicated things, but then you need much more data. So let's keep to this simply connected case maybe for now. Yeah, I wrote it there. Okay, so it turns out that there's another crucial property that we kind of already observed while exploring this interface. And given those two properties, we can almost characterize this object. And that was somehow how SLE was defined. So I didn't tell you anything about SLE yet. I was just talking about this discrete models. But it's very useful usually to think about discrete model, even if you work on continuum things, because you at least you get some intuition. So let's see. So Oded Schramm was asking how to describe these kind of curves. And he also already had been reading physics literature and had been expecting that this conformal invariance property would hold. So what else? So there's another property, which is some kind of a Markovian property. So maybe the idea is this exploration of maybe on the discrete kind of gives, we call it the domain Markov property because it depends kind of on the domain called DMP. So what does it mean? So let's say that I observe my lattice path. So now I'm yet in the lattice up to some, I don't know, n steps, 1, 2, 3, 4, so on. Up to there. There's some natural time, right? So each step is maybe one time unit. So then let's say given what I have, so now I write in this way, like 0n, n first steps. So what is then, let's say maybe law of the rest. So the rest would be then like n plus 1 onwards. And now I should say, I don't know what to put here because, yeah, I didn't parameterize it. So there's some kind of number, which is the ending time. Maybe let's say it's, for these purposes, is some capital T. It's a bit of a nuisance to keep track of it. So then what I mean is that if I found that the piece of the interface was going here, so what do I know about the rest, which is this piece? And now, if you think in terms of this, what was happening in this model, so the constraint was this Dobrushin boundary condition, right? And then how is the exploration done? It's just that you follow the dual edges between the pluses and minuses. So then if I followed, I draw them in this way so it's easy to see. I know that the next layer here is all pluses and here all minuses, right? But now I could actually look at the domain minus this slit, and this is still a simply connected domain. So you could note that D minus, what should I say? I guess kind of this. And now, if you're very careful, in the discrete, you have to be a bit mindful of what you erase. But the point is that I erase the slit, and I look at the complement. So this is like d minus gamma up to time n. So this is again a simply connected domain if you set it up in a good way. And it has Dobrouchin boundary condition. Let's say Dob BC, right? But now the marked points have changed. So instead of the B, I'm gonna have the boundary point here, which belongs to the boundary of the slit guy, right? And now if you think about how this was set up from the Ising model, so if I already found this piece, so what is in the complement is just the usual Ising model, but with this modified domain, right? I'm gonna keep the picture, but erase this. So then we get the answer to the question, right? I don't know if orange is different enough, but orange would be this thing. So then we decide that the law of the rest, which is from time n to whatever, is the same as, maybe I'll use Ising interface in, let's see, d minus this thing that we already found. And from gamma n to a. Actually, maybe that should be b. Yeah, sorry. And that should be a. If I want from a to b. It actually doesn't matter, but I think earlier I said it's going from a to b, so maybe it's better to do it this way. So that's the yellow piece, right? And now if we somehow would take the limit, this is again a big kind of question mark. I would say that what is this law then? Is this probability measure on there in the slit d minus. So now I need to have the continuum guy there up to some time. So now there's some kind of difficulties if you want to make this precise, because the time unit step, you know, is not going to work anymore after the limit. But the idea anyways is that you just get, so maybe here I put t, little t like time, and that's somehow related to the n. And then it's going to go to, still to b if it was on the boundary. Or maybe these a and b are changing a bit if the lattice is changing, depending on the setup. So the point is that I can transfer this property that was in the discrete is kind of evident, right? From how I set it up. With a big question mark, I can transfer that to a property of the limiting guy. So this is now without delta over here. And it's a very natural property, at least for this model, right? And actually here, it didn't really matter what this temperature was. What only mattered was that I can explore, then I can stop, and I can look what's after that. And it has a similar form, but in this slit domain. And that's the main reason I chose the Ising model for like the prototypical example, instead of, say, the discrete Gaussian free field, for which you can define 0 level lines. But this property is not evident there, so I couldn't figure out how to motivate this from there. So here it's just completely obvious, right?
So to be precise, it's the law of this gamma delta nt conditioned on the...
Yes.
Right.
Exactly. Thank you. Conditioned on this initial part, obviously, because I need that information in order to form this slit domain. Yeah, thank you. So I kind of sketched that there are two properties that we expect. Does it make sense? Do you have any questions or comments? So what I'm about to claim you now is that those two properties are very strong, and they single out almost a unique object. That is this SLE guy that I'm trying to define to you. And somehow what's the remaining piece of information is how did this depend on which critical model we are looking at, except that I was setting up in this way using the Ising model. For instance, you could have the critical Potts model, which has more spins or something like that. Or yeah, whatever is your favorite, maybe double dimer model. And you would expect actually in the scaling limit similar properties. So why is the interfaces in those models still not the same? Is that there is one kind of degree of freedom left. And that features in the SLE. I think you've seen it a few times mentioned already. So maybe I will put the definition / theorem, because you need to kind of prove that it makes sense. Okay, so now this SLE kappa, where kappa is some, well, it can be 0, but that's a bit trivial. Some positive parameter. So what is this? It's a family of probability measures. Proba measures, which is indexed by these domains. So now I use the same notation, D, A, B, and maybe kappa there. It's a bit complicated to write, but I'm trying to write it more precisely so that it makes a bit better sense. Indexed by D, simply connected. And then 2 boundary points, which are different. And well, the kappa is always there, such that.
And these are probability measures in spaces of curves in D that start
Exactly.
at A and end at B, right?
So maybe the caveat here is, yeah, can put it here, because I just wrote this already, kind of. So you need some topological space or Polish space. So this star means on, let's say, gamma, yeah, unparameterized. I often have the time, but actually it will not matter, curves. And then each of them is in this domain, so I should say in D, maybe from A to B. So you could pick some parameterization, and then maybe gamma times 0 would be A, and gamma time, I don't know, capital T would be B. And then with some topology, right? Some topology that you can put. For instance, you just compare curves up to reparameterization. Or you can actually consider them parameterized, but then you have to fix a bit more things. But let me not go there. You can find it in various places. Okay, so you can intuitively think in this way, like they come from somewhere. And so yeah, okay, there's a bunch of measures I can put in this space. So what is the key feature? Is that we have the 2 properties that hold. So such that maybe, yeah, 1, conformal invariance holds. I will maybe not write it again. It was meaning that you can transfer by push forward. And then the domain Markov property holds. So you can say that for any times, so now for any times and for any parameterizations, I would look at the law of the curve like after time t. Maybe let's say parameterization in this way. And let's say given, yeah, this notation is invented, but I hope you will kind of understand what it's supposed to mean. The conditional law of the remaining part, given the initial piece. Well, now I need more maybe info. Let's say is P D minus that thing. But now I'm cheating a little bit because maybe there's some caveats happening here. I'm just repeating what we kind of found. So I should assume that here the gamma is exactly in the initial kind of domain. So hope it makes some sense. It's not completely precisely written here. B. Yes. Sorry. Yeah, the target point. Yeah, so I can draw it again because I need to tell you why this makes sense. Like, why is it a good definition? And there maybe you see the picture a bit better again. So it's kind of a Markov property because you kind of observe up to some time, little t. And then you ask what's happening in the future. So this is somehow what this law is supposed to mean. And then the claim is that the future has the same type of law, but I need to modify the domain. So that's why the Markov property has the D in it, kind of. Yeah. I'm missing a lot of parentheses. And so the claim is that this is a good definition. That's somehow the theorem part. So maybe, let me see how to explain it. So why is it well defined? Right? So first of all, if we assume this conformal invariance property, then we already can pick our favorite domain. So it suffices to take. So now my favorite domain is not going to be the rectangle anymore because it's easier to write stuff in a different domain, which is the half plane. I think you saw maybe this picture already. And then the curve is going to grow from 0 to infinity. A is 0 and B is infinity. So infinity is the boundary point of the upper half plane, right? Because any other triple I can get using the conformal invariance. So that's one question. Observation. So then question is kind of why this other property singles out a one parameter family of measures. So then they are this kappa, right? 0 infinity. Often there's a semicolon, but I always forget it. So kappa in any positive. So that's the remaining kind of question. So if I can argue that imposing also the Markov property with a modified domain actually only leaves one kind of degree of freedom, which is a positive parameter, then I've shown you that this definition, makes sense. And so the theorem then would be formulated that there's a unique probability measure with these two properties. Question?
So I guess not only the domain Markov property, like the conformal invariance still.
Yeah, you will actually need it still. Yeah.
Because you can map the upper half plane to itself, and right, still.
Yes. Indeed. So I should also say plus scale invariance in the half plane. Because even if I fix two boundary points, I still have a scaling that I can do. And that is actually important. So you really need both properties for this. But somehow there it only becomes kind of more restrictive if I consider the half plane. So that's maybe one good reason also why the half plane is a nice domain for this question. While it was not so nice for the Ising model because it would be an infinite unbounded domain and I didn't want to even try to draw a grid there. So yeah. So this was somehow the key maybe result that Schramm was trying to prove. And he finally succeeded. So first he proved this classification in year 1999, I think. But he didn't manage to show that these objects are always supported on curves. So this is some measure on some growing sets that's kind of coming from the construction. It's actually very non-trivial to show that you get a curve, believe it or not. Somehow from this lattice path it sounds reasonable, but it's not easy to show at all. But so if we believe that these are supported on curves, then we can constrain how they look like. Now, still have maybe a bit less than 10 minutes.
The SLE, they are not curves or kappa.
Aha, they are, but okay, maybe before going to here, I can say what kappa does indeed. Yeah. So, because I can draw here. So, well, if kappa is 0, it's a bit stupid, so maybe we can just ignore it. I mentioned it in my talk. It's just becoming a geodesic. Then if kappa is between 0 and 4, 4 being the one related to GFF, then it's a simple curve. So it's somehow, it's fractal, but it's, simple. Simple or injective. So this is still kind of good. And Ising model, by the way, is kappa equals 3, so it's in this region. Then if you have the kappa bigger than 4, kappa is somehow the speed, how fast is turning this curve. You will see soon why. So one can show that in this region, up to 8, it is still a curve, but it's making some kind of self-touchings and touchings to the boundary. But I can always say that it's still, growing at one point. So this is somehow self-touching curve. And then for the remaining region, it's still a curve, but it's going to fill everything. Okay? So this is a Peano curve, space-filling curve. And now I'm not able to draw it. It's going to track everything like this. Okay? Yeah. And there are various models actually, so you might like some favorite models. So in this region we have what I was discussing is the Ising. Then maybe you like the loop-erased random walk if you heard about it. If not, just forget it. Then this is the GFF level line, whose definition is kind of quite intricate, but you can make sense of some kind of zero height line for the GFF, which is the object Nathaniel was describing. But the definition is quite difficult to do, so thought it's better to actually stick to the basics, what the objects are, instead of trying to define it. And then here, kappa equals 8 is the uniform spanning tree, the contour there. That's becoming space filling. In this region, it becomes a bit messy. Maybe you like percolation. So I will stop maybe for the listing there. But there's various models in all of these different regions, and they are meaningful. So, yeah, it's somehow the whole range. Maybe kappa go to infinity, it's a bit weird, because then it's kind of infinitely, turning infinitely much, and it becomes just somehow the growing Lebesgue measure in this way. So there's even, I think kappa equals 12 is some, what was it? Some kind of, related to some kind of obscure model for some oriented, what was it? Maybe you remember? Yeah, there's some kind of model. Yeah, something like that. Yeah, so anyways, there's a lot of examples. So somehow after you believe that there's some convergence proven, so most of these that I listed are lattice models, right? And then it's very difficult normally to prove the convergence from the lattice model to this object. It's been done for actually all these cases that I listed here. So then you can study the object in the continuum and maybe also learn some things about the discrete, like some critical exponents and things like that. So it's pretty useful just to, if you want to work on the continuum side, like I mostly have been doing myself, though I did some kind of discrete stuff also in my life. But so yeah, I think before finishing, maybe I need to say how do you, like why is this a good definition, right? And now I need a black box, which is this Loewner's theorem, let's say. So maybe you remember these observations are due to Schramm and others. And the tool that can be used is due to Loewner, so 1923. And maybe I just state in a bit simpler way. So given a simple curve, you can do it for the others, but for the sake of time, I will stick to the easiest case. I'm happy to tell you more about it if you want. And let's say we parameterize in some way. And I want it to live in the half plane because so I'm kind of interested in that. Well, first of all, there are conformal maps. This is trivial. I call them GT. Let's draw it here. For each time t, now I parameterized. So I can talk about the curve at time t. And now if it's a simple curve, I can always find a conform map from the slit. So this is exactly the idea that we've been already kind of using for the domain Markov property. So half plane minus the simple curve is simply connected. So I find a conform map back to the half plane. And then I can track where this point is going, and it's often called WT. So this is some real point. And yeah, a continuous function W. So when time goes on, the curve is growing, and then the image of the tip is moving, right? Continuous function W from the time parameterization to the reals. And the non-trivial part comes here. So there's a differential equation for the time evolution. And this is the black box that I don't have time to prove. It's not super difficult to prove. It needs some complex analysis. So the time evolution of these time indexed maps. So I chose some normalization, for which reason there's number 2 here. And then it's maybe slightly mysterious. So here's the difference of the image minus the W. So for instance, if I'm tracking some point Z, so I need to say that, you know, there's a lifetime only up until the Z is somehow hit by the curve. So then it goes to some GT of Z. And in this equation downstairs, there is the difference of this point to that. So there's some blow up, hope you can see it, when the evolution of the point hits here. So this is up to some blow up time. But this is an ordinary differential equation. And maybe it's obvious that at time 0, nothing happened. So I have an initial condition in time. So this is the initial value problem, right? And now you can somehow ask, what does this domain Markov property impose for what kind of objects can I observe? So remember that it was saying that the future of the curve has a similar law, but in the modified domain. I think I erased it already. And now if you think about it, and I need scale invariance, you will find the following. So since I'm running out of time, I will just describe briefly. So if I look, what can this W, so this is going to be a random variable. So WT, this is actually a stochastic process, right? Because the gamma is random. So now I want the simple curve to be this satisfying these properties. Okay? And then I want to deduce properties of this W. Because if I know the W, I can solve the initial value problem. So W appears here. But if I know it, I can find these G's by solving this, by Picard-Lindelöf theorem. And then I can get, for any time t, where is the tip of the curve. So I got the curve then. So somehow all I need to know really is the W. It's a little bit quick, but the upshot is that I really need to find a one-dimensional stochastic process in order to characterize my object. And let's see, so what does it mean? So if we have the future has a similar probability measure, similar law as, you know, the actual thing in a modified domain, if you make a tiny increment, you expect that it should be somehow independent of the previous increment and somehow stationary, because for any time t, I can do this. So if you think a little bit, you find that you must have stationary independent increments for this W process, which already looks quite nice, because then there's a result in probability theory saying that in that case W has to be Brownian motion plus a drift. So Bt plus maybe some alpha t and maybe some speed. I will already put kappa here. Okay? And I just need to say that the drift is not there. And then I'm done, because then the SLE is given by this thing. And somehow the scale invariance, if you compute, it gives some properties for the W, which is exactly the Brownian scaling, actually. So this is a bit non-trivial. So what is it? So lambda times E over, is it like that? Has the same law as the W, something like this. And if we know that, that will show that the alpha is 0. Okay, so if you're not a probabilist, this is probably not super clear, but the point is that there's some basic probability theory arguments that tell you that the W, this driving function, has to be Brownian motion times some speed, kappa, which was this additional parameter. And now you can somehow backtrack everything to say that this is the only possible object you can have somehow. And then, yeah, you can ask what happens in the other cases and so on. But I will leave it to this, but I'm happy to explain more about any of these aspects at any later time. So just come grab me. Thanks.